This is our Chapter 11 video about polyprotic acid-base equilibria. Now, polyprotic just means that there is more than one hydrogen involved. And so what that means is that we are going to deal with acids or bases that can either donate, that would be the acid, or accept, that would be the base, more than one proton. Proteins are really common examples of this. And proteins, their activity are pH dependent because they are polyprotic. Now, proteins are made out of amino acids, and amino acids have these functional groups that make them very dependent on pH. So I'm actually going to look down here. Amino acids are examples of these things called zwitterions, which is a molecule that has both a positive and negative charge on it. So if we look at this example here, we have something with a positive charge and we have something with a negative charge. So the overall charge is still neutral, even though there are areas of charge on the molecule. And why that makes amino acids and therefore proteins so susceptible to pH change is because, down here, at low pHs, both the ammonium and the carboxylic acid, the carboxyl group, are going to be protonated. So they're going to have the hydrogens on there. At high pHs, so that would mean not very many hydrogen ions, neither group is going to be protonated. And then kind of in the middle between, you're going to have the carboxylic acid group sometimes protonated and sometimes the ammonium group protonated. So depending on which pH it's in, this molecule, this amino acid, is going to have a slightly different structure. Now we're going to use an example of the amino acid leucine, and we're going to abbreviate that HL. And that HL stands for a hydrogen ion on the basic form of the leucine. And what we can see here in this schematic here is basically what we were talking about in the slide before. At low pHs, so that's where there's a lot of hydrogen ions, the ammonium group and the carboxyl group are both protonated. Kind of at moderate pHs, so kind of in the middle, one will be protonated and the other isn't, and that at high pHs, where there is very little hydrogen ions, this is going to only have one, so it's lost one of its hydrogens, and this isn't going to have any hydrogens. So in this case here, neither of them are protonated. Now this can get pretty complicated because the picture is pretty clear. At low pHs, we're going to have mostly the protonated form, and the picture's fairly clear. At high pHs, we're going to have the totally unprotonated form. But at anything other than extreme pHs, we're going to have some equilibrium of all these things. And so what we can really look at this is if we look at it as an acid, it's a diprotic acid. It has two hydrogens. The first equilibrium is it losing one of its hydrogens, and then the second equilibrium is it losing the second hydrogen. So there's actually two Ks that are associated with this equilibrium. Now, as always with acid-base things, we can look at things as an acid like we just did. We can also look at it from the base point of view. So if we look at this as the leucine anion being a base and it getting protonated, so getting one hydrogen and then getting another hydrogen, there are two equilibria again. Here, it's getting its first hydrogen, then it's going from its monoprotic form to its diprotic form, and that would be getting its second hydrogen. And here, if we're looking at it a base as a base, there would be two KBs. Now, when we're comparing the KBs and the KAs and kind of seeing how they link up to each other, I want to kind of show you that if I'm just going to kind of concentrate on this reaction first. This is the reaction between L- and HL. So the equilibrium is between L- and HL. If we look onto the acidic side, the relationship between L and HL is Ka2. So Kb1 and Ka2 are talking about the same equilibrium from different points of view. And that's why they multiply together to be Kw. if we do the same thing with the other reaction, so we're looking at the equilibrium between HL and H2L. Here, H2L and HL, it's Kb2 and Ka1, and that's why they multiply together to equal Kw. So that's going to help us when we need to start converting between Kb's and Kas, or when we have a Ka but we need to find a Kb. Now I threw this slide in so that we can use it for a reference point later on if we need to look up Kas, if we're doing problems and things like that. And also just to kind of show you the range of Kas that we would be working with. Here we have our amino acids, and then we have the pKa of the carboxylic acid group and the pKa of the ammonium group. And to kind of look at the variation here, for the ammonium group, the pKa, the highest one on this list was 10.7, the lowest one is 8.67. That's about a 3 pKa point here. For the carboxylic acid, the range is quite a bit smaller. The lowest here is 1.6, and I think the highest that I saw was 2.4. That's less than 1 pKa unit. So the carboxylic acid groups vary less than the ammonium groups. So I'd like to run through some calculations, and the way these are organized, we're going to do 3 calculations, and what they're kind of centered around is what the most prevalent form of our polyprotic acid or polyprotic base is. So the first calculation that we're going to do is what if we have some numbers and we were talking about something that is mostly in its totally protonated form. So that's the first kind of calculation we're going to do. And then we're going to talk about what if it's in its totally unprotonated form. How are we going to find the pH of a solution in that situation? And then we're going to talk about the more complicated one is what if it's in equilibrium and it has a little bit of everything, but it's mostly in its intermediate form. So like I said, the first thing that we're going to do is we are going to talk about how to find the pH when a polyprotic acid is in its mostly protonated form. Okay, so this is the example that we're going to use our leucine here, and I've put in the pKa's and I found the K's from those pKa's. And then I've just we're going to go through the process and we'll put some numbers in. Right. So if we're talking about the acidic form that's mostly protonated, the H2L, it's a weak acid. I can tell that from its K, right? It's not like close to 1, that would be a strong acid. This is a weak acid. And if the H2L is a weak acid, it means that this one is an even weaker acid. And we can tell that. That's true for almost every acid, but we can also tell that from the K's. This one is so much higher than this one. So this is the stronger acid, this is the weaker acid, and this isn't an acid anymore, it's just a base. So when that's true, when the K's are so far apart from each other, say more than 1,000 away from each other, we can say that the protonated form behaves basically is a monoprotic acid. It does make the intermediate form, but the intermediate form barely makes any of the basic form. So this equilibrium is the most important one to us. So we're going to find the pH of 0.05 molar leucine hydrochloride, so that's the H2L+, and it gives us the Ka here. The first thing that we want to do is we want to kind of organize our data. We are trying to find the pH. To get to the pH, we need to find the hydrogen ion concentration, and what we usually do to find that is we use something like an ice table. So that's going to be our first step here. So I'll set up our ice table. I'm going to say that it's H2L, and this is going to be the HL, like this. If we do an ice table, initially there's 0.05 of this, none of this. Some is used and added to the product side. Okay, and we know that Ka is equal to now x squared, the products over the reactants. All right. To solve this, I mean, we have the Ka, so we know that that's equal to 4.7 times 10 to the negative 3. But to solve this, we would have to use the quadratic unless we can say that plus x or minus x is small compared to the initial concentration. To make that judgment, we would take the Ka, and if it times 1,000 is still less than 0.05, which is the initial concentration, we could say that plus x or minus x is insignificant there. But that's not going to happen for us in this case. We're going to get really close to that 0.05, so I don't think that that's a good assumption for us to make there. So we're going to have to use the quadratic. I'm going to say that we're good at the quadratic, and I solved it for us. I found that x was equal to 1.32 times 10 to the negative 2. And so x is equal to the hydrogen ion concentration, and we would find that the pH, so pH is negative log of the hydrogen ion concentration, and when I did that, pH was equal to 1.879. Now that's the pH. This is the pH. If the only equilibrium that we really have to worry about is this one here, and we don't have to worry about the one of HL going to L minus and H plus. And so we made that assumption at the beginning to simplify our calculations. The way that we can tell that that assumption is true or not is by looking at the relative concentrations of H2L, HL, and L minus. And if the H2L is, quite a bit higher, and even more, if the HL is much higher than the L, we know that this equilibrium really wasn't happening, and that assumption that the most important equilibrium is just this one, it basically stops at this point, will be true. So let's go ahead and calculate those concentrations so that we can decide if our assumption was valid or not. So again, we're checking the assumption that the HL concentration, this guy here, is going to be much higher than the L minus. And that'll tell us that this equilibrium didn't happen. Now from our last slide, we found that at equilibrium, so that was the end of our ice table, the H2L was the initial concentration minus X, and that the products were each X. So if we're trying to validate our assumption, and we're trying to find the concentration of each one of these, we can find the H2L because we know that that's true. So 0.500 minus, and the concentration we found of X was 1.32 times 10 to the minus 2. That is, and there's supposed to be a 0 in there. So that should be 0.05. That is 3.68 times 10 to the minus 2. Now, that's going to also allow us to get to the HL concentration. And what I mean there is we already know the concentration of the HL. We did that when we found X. So that's 1.32 times 10 to the minus 2. Those numbers aren't that different from each other. And what that tells us is that, yes, this is a weak acid, but it's a strongish of the weak acid. For almost every 2 of these, or maybe every 3 of these, it produces 1 of the HLs. Okay, the last one that we need to find, so we found our H2L concentration, we found our H concentration, but we need to compare those to the L minus concentration. So to find that, L minus is going to be a small number, probably, we're hoping that's our assumption, but it is going to be non-zero, right? It's not none of it is made. There is some kind of equilibrium. So to find that HL, to find the L concentration, what we can do is we can use the second K. So we're going to use the equilibrium that was on the other side here. And that equilibrium, so it was kind of over here on one of our first slides. The hydrogen wasn't there. And it said that the Ka2 was 1.80 times 10 to the negative 10th, and it's making L minus and H plus on this side. So we can use that K. We know that the K is equal to the products over the reactants, and so here Ka2 is equal to the products, L minus, H plus, over HL. Now I know it's really tempting here to say we know the Ka, and then these should be equal together. You want to say that because they're in a 1-to-1 ratio here. And then this is divided by the HL. We know that concentration. And so it's easy to solve for X. I just want to point out the flaw in that. It's true that we could solve for X, but the problem is that they are not equal to each other. I know that it seems like in that equilibrium they come out in a 1-to-1 ratio, but I want to remind you that the hydrogen concentration is not only this hydrogen here, but it's also the hydrogen that was made here. And so we know that concentration, 1.32 times 10 to the minus 2, that number is going to be way bigger than the number we would get for hydrogen if we put x squared in here and solve for x. If you do that, you get somewhere in like the times 10 to the negative 6 range. That's a very small number compared to this hydrogen here. So what we could do, I mean, in a perfect world, we would say that Ka2 is equal to L minus, and then the hydrogen concentration is 1.32 times 10 to the minus 2 plus x, and this would be x2, and this would be HL, and then we would solve for x, but that gets really complicated. And like I said, this number here is going to be much bigger than the x. So it's easier if we just say that plus x and minus x would not matter here, and we just kind of get rid of this. So that kind of cleans up our math a little bit. And like I said, I get that it doesn't look like we need to clean up our math, but the problem with saying that this is x squared is that we aren't accounting for that large concentration of hydrogen ions from the first equilibrium. So the better way of doing this is, yes, use your Ka2. And then we're solving for L. We're going to put in 1.32 times 10 to the negative 2 concentration for hydrogen, and then our H concentration is 1.32 times 10 to the negative 2. Those cancel out, and we get that the HL concentration is equal to the Ka. All right, to kind of summarize our findings there, we were trying to see if the assumption that there was very little, so almost everything was bigger than the L minus concentration, and we can just compare HL to L minus. The concentrations we got there are 1.32 times 10 to the minus 2 and 1.80 times 10 to the minus 10. Those are very far apart from each other, and so I would say that this assumption is true. So that actually just works us through one of the assumptions that we make all the time in 1B. In 1B, we assume that polyprotic acids behave like a monoprotic acid for losing their first hydrogen, but then almost nothing happens after that, which is why when sulfuric acid loses its hydrogen, it's a strong acid, but it's only the first reaction that's a strong acid. After that, we don't count it as a strong acid anymore. So kind of validating those assumptions that we make in 1B here. So the assumption that we're making is that the only Ka that matters is the first Ka. Even if you went through and didn't say that the plus x's and minus x's were insignificant. The error in pH is about 4% or 0.01 pH units. So for most calculations, that's going to be okay. If you're doing quantitative chemistry, maybe you want to be a little bit more careful about that and not make those assumptions, depending on how accurate you need to be. And then just a little plug for how we would apply this to kind of a basic situation. If you're looking at something like a base and you're applying the same kinds of assumptions, we would say that the only base equilibrium that matters is the first one. And so it's so much bigger than Kb2 that Kb2 almost doesn't matter, just like we said that Ka2 didn't really contribute much to this equilibrium here. All right, and so let's actually practice those base calculations. I want to do a very similar calculation. We're going to find the pH of a 0.05 molarity leucine salt. So that's the sodium leucinate. That would be like NaL. When you separate those from each other, that's sodium and L minus. And so we're just looking at this as the totally unprotonated basic form. So we're looking at this at the really kind of far end of the spectrum. And by far end of the spectrum, I'm talking about the high pH portion. So the high pH portion is when there aren't many hydrogen ions, and so it should be in its unprotonated form. So we're going to do something similar here. We're going to set up an ice table like we did last time. So this is the L minus, this is the HL charge. And so when the L minus reacts with water, it would get one of the hydrogens to make HL, and then the OH would be left over. Okay, so OH is going to be our other product here. We're starting off with a 0.05 molar concentration. And so this would be, we don't have any of those, minus X plus X plus X, 0.05 minus X. And so when we set up our table, this was a basic reaction, so we're going to have to put in Kb there, but it's X squared over 0.500 minus X. Now in our original problem, it didn't give us any Kb's, and so I just wanted to remind us what was given. So this was the kind of original equilibrium, like this. And originally we were told that this was 4.7 times 10 to the minus 3, and that's the Ka, and the Ka here was 1.80 times 10 to the minus 10. Right? So this is the equilibrium we're talking about. And so we can use that Ka to find Kb. Remember that the Kw of water divided by the Ka would get us the Kb. When I did that, I got 5.55 times 10 to the minus 5. That's a lot of 5s there. So this is 5.55 times 10 to the minus 5. We have X squared and minus X on the bottom. Now the good news is that our Kb times 1,000 is less than our initial concentration. Remember, we usually mark initial concentrations as F, like the formal concentration. So because that is true, we can say that this doesn't matter, that plus X or minus X essentially goes to 0. That makes it a lot easier. We don't have to use the quadratic. And when I solved this, I got that X was equal to 1.64 times 10 to the minus 3 molarity. Now, if you remember what X actually means here, X is the hydroxide concentration, and we're trying to find pH. So we need to go from the hydroxide ion concentration, we could do POH, and then we could find pH. It's also possible to take another path. We could go to the hydrogen ion concentration and then to pH. Either way, you do it. I was just going to take this path. but you'd get the same answer regardless of which one of those you did. So what I did is I said that the Kw was equal, so Kw is equal to the hydrogen ion concentration times hydroxide, so Kw divided by hydroxide is equal to H. And when I put in my numbers there, I got that the hydrogen ion concentration was equal to 6.10 times 10 to the negative 12th molarity. And if I take the negative log of that to get pH, it would be 11.215. Now again, that pH is true if the only equilibrium that's happening is this equilibrium. So only the L being protonated one time to make the HL, but then the HL not getting protonated to make the H2L. So we're counting on that not happening. To check that assumption, we need to check the relative concentrations. So we need to find the concentration of L, L minus, HL, and H2L. And we need to show that this one is much more concentrated than this one. To find those concentrations, we can find the L concentration. L minus is 0.05 minus the hydroxide ion concentration, which is, when we calculated X, it was 1.64 times 10 to the negative 3. So the L concentration is 4.84 times 10 to the negative 2. Now, just like we did in the last problem, to find the and we know the HL concentration because we found that that's 1.64 times 10 to the minus 3. So we have this one and this one, but to find this one, we need to talk about that next equilibrium. So it had a Ka that was given. It was 4.7 times 10 to the minus 3. Yep. And that's when it was making its H2L. So we can use that Ka to find Kb, and then we can use an equilibrium expression to make sure that those concentrations work out there. So the Kb is equal to, this would be X, so it would be the H2L times hydroxide ion concentration over the HL concentration. I'm just going to clean this up a little bit. And again, remember, in the last one, we wanted to say, I see students doing this a lot, saying that those two are equal to each other, they're each X's, but that's not true because we made so much hydroxide from this equilibrium. So we can't say that those are in a 1-to-1 ratio. What we can say is that the Kb is equal to the one that we want to find, and then we put in our X concentration for the OH, 1.64 times 10 to the minus 3. And the HL was on the bottom, and that's 1.64 times 10 to the minus 3. And those cancel out just like they did last time, and H2L is equal to the Kb. I found the Kb the same way that I did finding the Kb for this reaction. I used the Ka, so I went from the Ka to the Kb, and I found that the Kb was 2.13 times 10 to the negative 12, and so that is equal to the H2L. All right, let's compare those. We wanted to say that the HL was very big compared to the H2L. So is the HL big compared to the H2L? Look at those exponents on the 10 there. I would say that those are very different from each other. This one is so much higher than this one. So what that means is that our assumption was validated and that this is the only equilibrium that matters. It never went on to the second one, so we didn't really have to count those numbers. So now I'd like to talk about how to find the pH when we have some information about an equilibrium where the most prominent form is the HL form. So remember, this is going to be a little bit more complicated because HL is amphiprotic. It can be both an acid and a base. And so we need to take both of those equilibriums into consideration. When we look at the K's over on this side, and we look at the exponents here, this one is higher. So this is a higher Ka, and this one is lower. What that tells me is that since the Ka is higher than the Kb, I would expect the solution to be acidic. So we're probably looking for a lower than 7 pH, probably. But because these two numbers aren't that different from each other, they're only 100 different, we can't totally ignore that base equilibrium. What this means is that there's going to be a lot of equations. There's going to be at least 2 equilibria going on, a lot of equations, and the way that we handle lots of equations is we use the systematic treatment of equilibrium. So that's what we're going to do for this problem. Now I've out the steps here. The first step in systematic treatment of equilibrium is to write out the reactions. So I did that. These are the acidic reactions, and these ones were the basic reactions. And when we look at these K's, I'm going to just kind of remind you that that's Ka1, Ka2. These already had the B's in there. All right, step 2 is to write a charge balance. Remember, a charge balance means putting everything that's equal, everything that's positive equal to everything that's negative. So the positive things are the H2L and the H. And we have another H2L over here. So H2L plus the hydrogen ions. And then we need to put everything that is negative on the other side. So our negative things are the L's and the OH's. That. And the next step is to do the mass balance. And there's a couple different ways that you can do mass balance. One of the ways that we learned about was setting the initial concentration equal to each one of the parts. And for here, they all have the L in them. So there's a couple different versions of the leucine ion. It's basically not protonated, protonated with 1 hydrogen, protonated with 2 hydrogens. And so out here, I'm just going to say all versions of L-containing compounds. It's not right. And so when we do that, it's going to be the initial concentration. A lot of times we write that just as an F, like the formal concentration. And all the versions of the L-containing compounds are L, HL, and H2L. So I'm just going to write them like that. And the next step is to write equilibrium constant expressions, 1 for each reaction. So again, I'm just going to remind you that that was Ka1, Ka2. And so if you do products divided by reactants, you would get this guy right here. And then Ka2 right here. If you do the products divided by the reactants, you would get that equation. And then if you did similar things for the basic reactions, we have this guy right here and this one right here. So it doesn't matter what order you write them in, we just need one equilibrium expression for each one of our reactions. All right, so we are at the solve step, and that always seems like a joke to me because it seems like just one little step that we're on, but it is really quite complicated. So there's going to be a lot of work. This is the biggest step. This is the most involved step. And it can be really hard to figure out where to start. So I just want to remind us about something that can help us keep our eye on the prize. The whole point of the problem is to determine the pH. And if we're trying to find a pH, the way that we can do that is we can use the hydrogen ion concentration. So as much as possible, when we're rearranging equations or trying to figure out what to substitute into something else, we're going to try and put things in terms of hydrogen ion concentration as much as possible. Okay, so that'll help us focus a little bit. So I'm going to start with our charge balance, which had hydrogen ions in it. And I'm basically going to try and find other equations that I can put in for each of these that have hydrogen ions in them. So what I've done is I've written our reactions from the last page, or our equations from the last page right here, all our K expressions, and then this one down here was the mass balance. Okay, so I've kind of what we can pick from on that side. One thing that I didn't put on that last page that we always have available to us is that the hydrogen ion concentration times hydroxide is equal to Kw. So we can kind of keep that in our pocket too if we need it. So what we're going to do is we're going to choose from these equations here what we can substitute into each one of these to get it more in terms of hydrogen ion concentration. For H2L, I was looking for reactions that had those in there, or that had H2L in there, and I saw a couple. I saw this one here, which has H2L. The problem is there's no hydrogen ions anywhere in here, so that has H2L in it, but it isn't a good substitute if we're trying to get in terms of hydrogen ions. One that I did see that had both of those requirements is this. It has H2L and it has hydrogen ions. So I'm going to rearrange this equation. I'm going to rearrange it so that it is H2L is equal to HL, hydrogen ion concentration, and then Ka1 would be on the bottom. So I just algebraically rearranged it there, and then I can put this in for H2L. So I've written that substitution in here. This is my H from right there. Okay. So now I need to do a similar thing for L-. I'm looking for a reaction that has L- in it and will also get me closer to say H+. The one that I see is right here. It has L- in it and it has H+ in it. So I'm going to rearrange that one. When I do that, I'm trying to get L- by itself on one side. So that would be Ka2 times HL divided by hydrogen ions would be L-, like that. So I'm going to substitute that in for L- because it's equal to L-. So I've done that there. And my next one is OH-. So I'm looking for anything over here that has both OH- and hydrogen ions. The only one I could think of was this one, which is that kind of one I added on the end there. That's what made me think of it. And so I'm going to reorganize this, kind of rearrange this one so I get it in terms of hydrogen ions. When I do that, I get that hydroxide is equal to Kw divided by the hydrogen ion concentration. All right, so I'm going to substitute that in for the OH. All right, so now things a little bit more complicated. We have things in terms of less. We have the system in terms of less things. We went from having 1, 2, 3, 4 variables to having 1, 2 variables. So that's good. That's progress. But now we need to kind of figure out how to solve this with those 2 variables. One thing that I see is I see some hydrogen ions on the bottom, and I want to get rid of that. So what I'm going to do is I'm going to multiply both sides by the concentration of hydrogen. So when I do that, I'm multiplying on both sides, so that's fair game in algebra. It's going to cancel out these guys, but it's going to go on the top for these ones. So when I do that, what happens is I get H plus squared on this side, HL, H plus squared divided by Ka1, but it gets rid of some fractions on this side. So this guy got canceled out with that one, and then just Kw on that side. So that simplified things a little bit. And now I see that I have two H squareds on this side. So what I'm going to do is I'm going to pull those H squareds out and kind of like we're factoring a little bit. So if I pull the hydrogen ion concentration out front, it's HL divided by Ka1 here. And nothing changes for this side. And I think I needed to pull that out like that. Okay, so I pulled my H squared out front, and then I have it multiplied by this whole thing here. What's nice about that is now, if I divide I have my H totally on one side, so if I divide both sides by that, okay, on this side it cancels out, and I get that H plus squared is equal to this whole block over here. And what's nice about that is this is a number we have, this is a number we have, this is a number we have. We only have one variable. So I've set my H in terms of just one variable. So I did that. I rearranged and I kind of cleaned things up and got our one equation there. Something that I want to point out we need to take care of in the future, this is H squared or H plus squared, so at some point we'll need to take the square root. I don't want to do that right now. What I want to do is this fraction down here is making me a little uncomfortable. It's like a fraction and a fraction, so I want to get rid of that Ka being on the bottom. The way that we can do that is if we multiply. So if we multiply both the top and the bottom by Ka, here it would cancel out. And so when we multiply those together, those cancel out. When we multiply these together, we actually get a Ka here. And then I also need to do that, multiply it by both parts on the top. So I'm just going to clean things up a little bit and give myself some room to do that algebra. Okay, so what I have is that the H2, and then it's going to be Ka2 times HL times Ka1 plus Kw times Ka1. So that's doing multiplying here and here. And then on the bottom, it's going to be Ka and HL like that. So it feels a little bit more simpler there. Just kind of getting everything rearranged. Now I feel like I can take this square root of both sides to get rid of that. And when I do that, I get H plus is equal to this square root A1 Ka and HL on the bottom. And when I do that, I just want to be clear that's for all of it. So now we have a pretty clear equation, and there's only one variable, HL. The problem is, first of all, we don't have a concentration. The problem hasn't given us a concentration, but even if it did, that concentration would be the concentration of all the forms of the L, the HL, the L minus, the H2L. So we're going to have to make another assumption here. We're going to have to kind of decide what concentration we're going to put in for our HL. And something that I'd like us to consider is, just like I said, let's keep things in terms of hydrogen ions so that we can keep our eye on the prize. Another thing that I want us to keep in mind is that in the very beginning of the problem, we had some numbers that told us about the relative equilibrium here. At the very beginning of this problem, it said that acting as an acid, and that would be the Ka2 for the reaction. So acting as an acid, the K for that was 1.8 times 10 to the negative 10. And then if it was acting as a base, going in this, so this acting as a base means it's going to get a hydrogen ion, so that's going in this direction. And it acting as a base would be the Kb2, and that was 2.13 times 10 to the negative 12th. So if you look at the relative numbers here, times 10 to the negative 12th going in this direction, times 10 to the negative 10 going in this direction, neither of those are big numbers. Those are both really small numbers, which means that whatever concentration we have is going to mostly reside in this form. So we can say that whatever the initial concentration is, it's going to be pretty close to the concentration of this. Not much of it went in this direction, not much of it went in this direction. It mostly stayed right here. So if we look at how that information helps us with this, is that the HL is going to be pretty much equal to the initial concentration. So I'm just going to substitute those in. H plus is equal to Ka2 times the initial concentrations times Ka1 plus Kw times Ka1 divided by Ka plus the formal concentration. So those F's are the initial concentrations, whatever they give you in the problem. So I've cleaned things up a little bit, and now let's actually solve for this. So we're going to determine the pH. All the other example problems we are doing, the initial concentration that we started with was 0.0500 molarity. So let's just use that here, and we'll put that in for our concentration. So I'm going to do my work up here. And to do that, I need to know my Ka2, my Ka1, Kw, things like that. So I'm going to kind of write those on the screen so that we have them available. All right, so this was our Ka2. This was our Kb2. What we're missing are our K1s and from the problems before. And so I'm just going to write these down. Kw is equal to 1 times 10 to the negative 14. And Ka1, I got this from a previous slide, was 4.70 times 10 to the minus 3. Now I looked that up, but we could have also used our Kb2 to find our Ka1, because we know that the Kw divided by Ka1 is, divided by Kb2 is equal to Ka1. So we could have also calculated it that way. So now let's actually put in our numbers there. I have that the hydrogen ion concentration is equal to Ka2, so that's 1.8 times 10 to the negative 10th times the initial concentration, times Ka1. That. And then we have 1 times 10 to the negative 14 and 4.7 times 10 to the negative 3. It's getting a little messy there, sorry. And we have our Ka1 on the bottom, 4.7 times 10 to the minus 3 plus 0.005. Oh, sorry. Too many zeros in there. And when I do that on my calculator, I get that the hydrogen ion concentration is equal to 8.80 times 10 to the negative 7. If we do the negative log of that, we would get a pH of about 6.05, 6.06. So that kind of makes sense when we were thinking about how this should probably be an acidic pH because the Ka was higher than the Kb. So that kind of makes sense in terms of the overall value we were looking for. Now, we should go back and just validate the assumptions that we started with in this problem. One of the things that we assumed was that the initial concentration would be roughly the hydrogen fluoride, or sorry, the hydrogen, the monoprotonated leucine like this. So that would be the initial concentration. So what we're saying there is that the concentration of HL is going to be much higher than the H2L concentration, and it's also going to be much higher than the L minus concentration. So let's validate those assumptions. Let's use our equilibrium expression to find these concentrations and then compare them to the HL. All right, to do that, we can use the first K's in the reaction. So this is one of our equilibrium expressions that we had when we were talking about systematic treatment of equilibrium. It's just a rearranged form of K1 equals HL, H plus, and then H2L, like this. So that's just rearranged. When we do that, and we use this equation, we find that the concentration of H2L is about 9 times 10 to the negative 6 there. The L minus, and what we're using there is the rearranged form of the K2. K2 expression, we find that the L concentration is about 1 times 10 to the negative 5. So let's compare those to what our HL concentration is. We said that it should be about the same as the initial concentration, which was 0.05. So that's 5 times 10 to the negative 2. So we're comparing that to these two and making sure that these two are much lower. And I would say that that's true. That's about 1,000 times different, about 10,000 times different. So I would say that those assumptions are pretty valid. So in doing that problem where we were given 0.05 of the formal concentration, and we said that it was mostly it was the intermediate form. Kind of to summarize what we found there is that the L minus and the H2L, they have pretty close concentrations, times 10 to the negative 5 and times 10 to the negative 6. So the two equilibriums were pretty close to each other, even though the K is bigger, the Ka is bigger than the Kb. That just tells you that it's not strong in either direction there. And we saw that nearly all the leucine remained in that intermediate form, that HL. What we have here is just a kind of summary of the three calculations we did, where we had 0.05 of the acidic form, and we kind of treated it that way and only used the first acidic equilibrium. We have it where we started off with 0.05 of just the basic form, and we treated it as a first base equilibrium. And then we have the intermediate form where we had to do a systematic treatment of equilibrium because neither of the Ka or Kb's were strong in either direction. They're both pretty weak equilibrium. So, and what we have here is kind of a summary of the pH and a summary of the concentrations that we calculated. Now, I did want to walk through a problem or kind of a situation that your book talks about. When you're dealing with this intermediate form HL, what we did was a systematic treatment of equilibrium. There is a more streamlined way if you make some assumptions pretty early. And so there's kind of this shortcut way that I wanted to go over. The systematic treatment of equilibria is always going to get you, a good answer. It's just that your book shows you kind of a shorter, more assumptions way, but it is a little bit shorter, so I thought we should go over that. All right. When we were doing systematic treatment of equilibrium, we eventually got to this equation here. And for us, we then just put in numbers for each one of these, and we calculated that the pH was somewhere around 6. If we look at this form and we make some assumptions, we can make it look a lot simpler, and we'll get to a point that you might have seen before. So let's go through these assumptions kind of one at a time. One of the first ones is that Kw is really small, 1 times 10 to the negative 14. And so anything you multiply it by is still, it's not going to be a very big number. So one of the things we can assume is that this part here is always going to be, almost always, going to be much bigger than this part here. And when you think about it like that, it's kind of like saying plus and minus x are not very big. And so what we're saying is that they are small compared to what we're adding them to. So if we assume that this portion here essentially goes to 0, then we're left with h plus is equal to the square root of K2, K1 times the initial concentration over K1 plus the initial concentration. Okay, so that simplifies it some. And then for these problems, if the formal concentration, so that's the initial concentration, if the initial concentration is really big compared to K1, and by really big, I'm going to say more than 1,000 times, and that's K1, sorry. And that was true for us because K1 was like times 10 to the negative 10th or sometimes 10 to the negative 12th, something like that, and the initial concentration was 0.05, so that's 5 times 10 to the negative 2. This K was, for us, depending, well, if we were doing it in an acidic or a basic one, for us, this was times 10 to the negative 10, I believe. Yeah, it was 1.8 times 10 to the negative 10. So, yeah, it's true. For the initial concentration, much bigger than this. So if we do that same thing again, we're saying that the formal concentration, the initial concentration, is big compared to this one. We can also say that pretty much this cancels out. Or maybe not cancels out, but it's negligible. All right. So when we do that, we get that the hydrogen ion concentration is equal to K2 times K1 times the formal concentration over the formal concentration. Those cancel out now. And we get that the hydrogen ion concentration is equal to the square root of K2 times K1. Now, if you take that equation, and I'm just going to move it up here so that I have a little bit more room to write, like this. If you take the log of both sides, and so I'm going to say take the negative log of this, and on this side, it would be the way that the math works out for taking the log of a square root is this would be 1/2 minus log of K1 minus log of K2, like that. Now it seems like a weird thing to do, but what I'm doing there is if I do the negative log of the hydrogen ion concentration, what I'm finding is pH. And on this side, it would be 1/2. Negative log of K1 is pKa1. And negative log of K2 is pKa2. Okay, so those are on the inside. All right, so what this is telling us is that we can straight find the pH by just using the pKa's and not having to do any of this shenanigans over here, okay? Now, this is an equation that you might have seen. So this equation here is an equation that you might have seen in 1B. It's an equation that we just kind of tell you is true. What we say is that the pH of an intermediate form of a diprotic acid is close. It's about midway between pKa1 and pKa2. Right? So that's an equation that we use that gets us pretty close to the pH that we would have found using the systematic treatment of equilibria. And so again, this is a good equation to use when your initial concentration is relatively high compared to your case, which is true for a lot of situations. So this equation is true when that's true. If it's not, the systematic treatment of equilibrium will always work also. Now, we just spent a lot of time calculating pHs, but if we look at things from a different point of view, if we're trying to figure out what is the principal species in the solution, and we know the pH, we can compare that to the pKa values, and that'll tell us what is the predominant the principal species in solution. So to determine the principal species, we compare the pH of the solution with the pKa values. All right, and let's look at this chart over here. If the pH is smaller, it's lower than the first pKa, we're going to have mostly an acidic, the principal species being the totally protonated form, so an acidic form. If the pH is somewhere between the pKa, the pK1 and the pK2, we have the intermediate form. And then if the pH is higher than the pKa2, we have the totally basic form. So that's how we can kind of get a snapshot of what's going on, what part of the equilibrium the solution is in by comparing the pH to the known pKa values or pK values. All right, to finish up this chapter, I want to talk about polyprotic acid-base titrations. Now, your book does an example of an acidic titration, meaning you have an acid solution and you track the pH by adding base. And when that happens, the graph that you get has two inflection points like this. So this would be base added, and this would be pH. Okay, so that's the example that your book does. I thought that I would do an example of the opposite, maybe give you another point of view. So we're going to look at this one here, so this graph down here, and what it's of pH on this side, just before, but we're starting with a base, and as we go along here, we are adding acid. Okay. So what we're going to do is we are going to find the pH at some kind of points along this titration curve, just kind of practicing our acid-base titrations, but applying it to a polyprotic system. So the system that we're going to be doing is a basic system, and we're going to say that we are going to add we're going to start off with 10 milliliters of a 0.1 molar weak base, and we're going to titrate it with 0.1 molar strong acid. These are the two equilibrium expressions, and so that's why we have two equivalence points. The first one is the base getting a hydrogen from water to make the intermediate form. And then the second equivalence point is that the intermediate form getting a hydrogen to form the totally protonated form. to be able to do this problem, we need to know the K's here. So the example that we're going to do, the pKa1 is going to be 4.0, and the pKb2 is going to be 9.0. So just a little bit of practice for what that means. If the pKa1 is 4, that means the Kb is 1 times 10 to the negative 4, and it means the Kb2 is 1 times 10 to the negative 9. Right, and the points that I want to do, I want to find the pH at different points where I've added different amounts of the HCl. So the first point that I want to do is A, and that is at the very beginning of the reaction before I've added any acid. Then I actually want to do some kind of point between A and B, just so we can get some practice. Then I want to do it at point B. I want to calculate the pH at point C, point D, and point E. So we're going to do each one of those, and I'm just going to, here, this is when we've added 0 volume added. Here, I'll just say we're going to add 1.5 milliliters of the hydrochloric acid. B is when we've added 5 mils. C is when we've added 10 mils. D is when we've added 15 mils, and E is when we've added 20 mils. And what we're doing there is we're kind of pretending that we don't have these pH numbers off to the side. We're actually going to calculate those, and then we can use this graph to check ourselves. All right, one of the things that we did at the beginning of our titration calculations in the other chapter is when we had these volumes, so the volumes that we're going for are 0 added volume, 1.5 milliliters, 5 milliliters, 10 milliliters, 15 milliliters, and then 20 milliliters. We kind of gave ourselves a rough check, like which one of these, if any, is the equilibrium point, which one's halfway in between the equilibrium point. Those would give us some shortcuts if we knew where they are. So the first thing that we're going to do is we're going to figure out how much the volume for the first equivalent point. Okay, so to do that, we know that we're starting with 10 milliliters of the base. We know that it's for every 1,000 milliliters, it's 0.1 molar. That's actually 0 in there. That was the molarity. We know that they react in a 1-to-1 ratio. And so that's of the HCl. And then the HCl was 0.1 molar also, so that's 1,000 milliliters, and it comes out to be 10 milliliters. So at 10 milliliters of HCl added, we know we've gotten to the first equivalence point. Now another way to do that is kind of this calculation here, where you're saying the moles are equal to the moles. They're in a 1-to-1 ratio. That tends to be how your book does it. I'm not a big fan of doing it that way, because what if they aren't in a 1-to-1 ratio? What if it's, a base that, well, I guess we're doing it 1 by 1, but I like to do my stoichiometry out in kind of a dimensional analysis way instead of this way. That's just kind of my flavor of how I do it. But I wanted to show you that you could do it either way. Okay, so now that we have the equivalence point, I'm going to go back to our last screen here, and this one here is our first equivalence point, which means twice that should be our second equivalence point. Okay, so those are going to be important. And we know some information about, these intermediate parts. Okay, so this one and this one here. We're going to have a buffer region, and then halfway in between the two equivalence points is kind of a special scenario too. Okay, at point A, that's when 0 milliliters has been added. And essentially, this is just a weak base system. So we have a base reacting with water. The Kb was 1 times 10 to the negative 4. And the best way to handle this would be to do an ice table where we start with 0.1 molar here, none of these. We do minus x plus x. And we say that the Kb, which is 1 times 10 to the negative 4, is equal to hydroxide, the protonated form of the base, over the base concentration. So that would be x squared divided by 0.1 minus x. Now, that's going to be a quadratic unless we assume that plus x or minus x is inconsequential compared to that 0.1. And the way that we compare that is we take the Kb times 1,000. If that's still less than the initial concentration, we can say that plus or minus x is negligible. So that's true, that they're actually the same there. So I'm going to say that this one doesn't matter. And then when we solve for x, we get that x is equal to 3.16 times 10 to the negative 3. Now remember, x is the hydroxide ion concentration, and what we're trying to find is the pH. So what we can do is we can go from OH to H by using the Kw for water. To do that, we'd use this equation. We have this one. If we rearrange Kw divided by OH, those cancel out. And so if I take the Kw and I divide it by the OH, I would get the hydrogen ion concentration. When I did that, I got that the hydrogen ion concentration was 3.12 times 10 to the negative 12th. And then when I took the negative log to find the pH, I got that the pH was equal to 11.49. So that makes sense. It's a basic solution. It should have a high pH. So just to summarize there, because it's a weak base system, no acid has been added. We use an ice table and the Kb, and we find the hydroxide, go from hydroxide to hydrogen ion, and then hydrogen ion to pH. So now we are at some point between point A and point B, and I said that I wanted to be when we had added 1.5 milliliters of the 0.1 molar acid. Now between the initial and the first equivalence point, it's a buffer problem. And what's nice about a buffer problem is that we can use the Henderson-Hasselbalch, but in this case, we kind of need to know what the ratio of base and conjugate acid is. So to find that, we need to be able to do an ice table. It's the same reaction going to its intermediate form. And so what we need to do is we need to figure out at equilibrium what the concentration of the bases and the acidic form is, and then we can put that into the Henderson-Hasselbalch equation because it's a buffer. All right, so initially we had, so in this ice table here, we have our 10 mils of 0.1 molar base, and when we do the stoichiometry there, I want to make my ice table in terms of moles, not molarity. That's going to be important to me because the molarity is actually going to be complicated because we're adding volume, so the volume's going to change, so the molarity is going to change. Moles is an easier way to keep track of dilution at the end. So when I do my ice table, I'm going to do it in terms of moles. If I do 10 milliliters of a 0.1 molar solution, what I find, if I'm calculating moles, is that that is 1 times 10 to the negative 3 moles. And I need to spread this out a little bit. Give myself some room. So I have my hydrogen here and then BH over here. Okay, so I've added 1.5 milliliters of a 0.1 molar acidic solution too, right? A hydrochloric acid solution. So when I do the stoichiometry there to find the moles, it's 1.5 times 10 to the negative 4 moles. And I haven't made any of this yet because I'm in the initial stage. So now when I go on to my change, I look at these two, and whatever one's less is the limiting reagent. And that's what I'm going to subtract out. They're in a 1-to-1 ratio. So the 1.5 times 10 to the negative 4 is less. All the acid's going to be used up. And when I do this, 8.5 times 10 to the negative 4, all this is used up, and 1.5, so 1.5 times 10 to the negative 4 here. So now I have my moles of base left over and my moles of the conjugate acid that I've created, and I can use the Henderson-Hasselbalch and put those values in. And I'm just going to do my Henderson-Hasselbalch work up here just so that I have a little bit more room. Remember that Henderson-Hasselbalch says that the pH is equal to the pKa plus the log of the basic form over the acidic form. And for us, in this case, I'm just going to be a little bit more specific. It's going to be Ka2. The reason why I say that that's true is because we are in the first basic equilibrium. We're in Kb1. And if we're looking at things, we're trying to calculate pH, and we have to use a Ka to do that. The Ka that corresponds to Kb1 is Ka2. Those two multiply together to equal Kw. We talked about that in the very beginning of the video, and so that's why we need to use the information about Ka2 for our Henderson-Hasselbalch. That's the one that links up to the base equilibrium that we're in. Okay, so we're going to do that. To be able to find Ka2 the way we need to here, we're going to use Kb, we're going to use Kw, we're going to find Ka2, and then we're going to find pKa2 from that. Okay, so just to kind of show you the work there. Kb1 is 1 times 10 to the negative 4. I'm trying to find Ka2. Kw is 1 times 10 to the minus 14. So when I solve for Ka2, I get 1 times 10 to the negative 10. And I'm trying to find the pKa2. So I need to take the negative log of both sides. And when I do that, I get pKa2, and I get a pKa of 10. All right, so now I'm going to put that in right here. So pH is equal to 10 plus the log of the ratio of the base divided by the acid. So the basic form is a B. The acidic form is BH here. And so now I'm going to use so here I have my B, and here I have my BH. So I'm going to put those in. And I'm running out of room a little bit, but I'll try and write it right here. 10 plus the log. The B is 8.5 times 10 to the negative 4, and the acid is 1.5 times 10 to the negative 4. All right, so when I calculated my pH, I got 10.75. Right, and that makes sense. The pH should be going down from what we calculated before, which was above 11. So the pH is going down. That kind of goes along with how we understand the titration curve look to be. Okay, so to summarize, because we're in a buffer region, we would use the Henderson-Hasselbalch equation, and we need to use an ice table to be able to find the values to put into the base in the acid form. All right, now we are at point B, which is where we've added 5 milliliters. That is still a buffer problem, but even though it's a buffer problem, we can use Henderson-Hasselbalch, it's also special in that it is halfway in between the initial and our first equivalence point. So the point B just happens to be halfway in between, and that's a special point. We know that in the Henderson-Hasselbalch equation, when the ratio of the basic form and the acidic form are equal to each other, which happens at halfway. So when these are in a 1-to-1 ratio, which happens at the halfway point, that part of the equation goes to 0, and the pH is equal to the pKa. So this is, if we remember that shortcut, we'll remember that the pH is equal to the pKa, and we just calculated the pKa was 10. So we just did this one. All right, so the pH is now down at 10. It makes sense that it got lower because we're becoming more acidic as we're adding strong acid. And that brings us to point C, which is the first equivalence point. At the first equivalence point of a diprotic acid, the most prevalent form is the intermediate form. So when we have the intermediate form of the diprotic acid, and what we're saying there is that we've formed a intermediate form of a diprotic acid. We're like halfway there. So we form this stuff. We found when we were trying to find the pH, when we have the intermediate form, we talked about this equation right here, where we further made some assumptions from that point. So we talked about how you could use this equation. You could say that Kw was small. You could say that K1 was small compared to the formal concentration or the initial concentrations. But if you have all the numbers, you can just put them in. And the only thing that we need to do, so we have these Ks. The only thing that we need to do that might seem a little bit tricky is we just need to account for dilution here. We need to account for how the concentration has changed because the volume has changed. All right, and to do that, I'm going to just do my dilution calculations up here. So we started off with 10 milliliters of the base, and now we've added 10 milliliters of the acid, so we have 20 milliliters total. That's 0.02 liters, and we just need to account for that dilution when you do each one of these. So for dilution, I use M1V1 equals M2V2. For my base, I started off with 0.1 molarity and 10 milliliters of it. I'm looking for the new molarity now that I have 20 milliliters of it. And so my new molarity is 0.0500. So that is how my initial concentration of base has changed due to molarity, to the volume change. So I'm just going to write that over here so that we don't lose track of it. So that is how my concentration has been diluted. And then we already have the Ka2, but we need to find this Ka1 so that we can put it in there. And to do that, we need to kind of look at our equilibriums that we've been working with. So I want to remind you that I'm going to do my work up here again, that Ka1 times Kb2 is equal to Kw. I have Kb2, it was 1 times 10 to the negative 9. This is 1 times 10 to the negative 14. So if I divide both sides, I get that Ka1 is equal to 1 times 10 to the negative 5th. Okay, so now we have everything that we need to put into this equation. All right, we have that the hydrogen ion concentration is equal to Ka2, which is 1 times 10 to the negative 10th. We had to do that when we found the Henderson-Hasselbalch halfway between point A and point B. And this is 1 times 10 to the negative 5th. Okay, guys, I'm just looking at this. I'm just looking at my work up here. Up here, I said that I was dividing both sides by 1 times 10 to the negative 9th, but I accidentally wrote 19. That is not what I did on my calculator. So up here in my work, I wrote 19 for some reason, but it was negative 9. Okay, so this number is correct. I just made that little mark there. Okay, so back to our equation here. And then the formal concentration was 0.05. Okay, plus Ka1 times, so 1 times 10 to the negative 5th times 1 times 10 to the negative 14. All right, divided by 1 times 10 to the negative 5th times 0.05. Okay, and we take the square root of everything. When I did that on my calculator, I got that the hydrogen ion concentration was equal to 3.16 times 10 to the negative 8. And then when I take the negative log of that to get the pH, I found that the pH was equal to 7.50. Okay, so kind of went down pretty drastically there. That makes sense for it being an equivalence point. That's where the pH should change the most. All right, now we are to point D. Point D is halfway between the first equivalence point and the second equivalence point. And there's something special about those halfway points. We know at halfway points, okay, so at halfway points, the pH is equal to the pKa. You just need to make sure that you're picking the right pKa. Is it pKa1 or pKa2? Now to kind of keep track, the last time we did this type of calculation was at B. And at B, we said that we are at the first basic equilibrium, which links up to the second acid equilibrium. So when we found this halfway point, we said that the pH was equal to pKa2. That means that down here, we're in the KB, the second base equilibrium, which would link to the first acid equilibrium. And so here, pH is going to be equal to pKa1. Now that definitely gives us a little bit of a shortcut here. So this is going to be pKa1. Ka1 is 1 times 10 to the negative 5th. If we take the negative log of both sides, we would get 5. So the pKa1 is 5, the pH is 5. All right, so done and done. And we are on to our last point that we're going to do. Our last point is the second equivalence point. That's where all of our base has been made into a weak acid, and we just have to use that weak acid to calculate the pH. Now, if we're trying to figure out how much of the weak acid we've made, and so that we can do our ice table, I'm going to do a little stoichiometry up here. So we started with 10 milliliters of our base, and its concentration was 0.1 molarity. So if we do that, we get 0.001 moles of base that we started this reaction with. At the second equivalence point, all that base has been converted into the totally protonated form, so 2 plus like this. And so if we have 0.01 moles of the base, we've made 0.001 moles of that weak acid. And I just want to remind you that we started with 10 milliliters of the base. We've now added 20, so 10 milliliters of the base plus 20 milliliters of the acid gets us 30 milliliters. So that's how many moles are in 0.03 liters. So if we need to account for concentration, we're going to need to take that volume into consideration. So this is just a weak acid problem. We're going to use that acid that we've made and make an ice table out of it. So H2B2+, acting as an acid, would be giving up its hydrogen. If I make an ice table, this is how much 0.001 moles I have. and I don't have any of this yet. I do minus x plus x plus x, 0.001 minus x plus x plus x. And again, that is moles, not molarity. If I'm going to put this into a K expression, like I would, so Ka1, it would be x squared over, let me back that up, it would be the hydrogen ion concentration times pH over the acidic form, like this. Now each one of those is a concentration, and so I should probably account for that dilution, count for that volume before I put them into the equilibrium. Okay, so what I'm going to do is actually account for that volume in 0.0300 liters. I would get 0.333 molarity minus x plus x plus x. So I just converted things from moles to molarity there. And now I can put those into my K expression. All right. And remember, I'm talking about my Ka1 here, so that's 1 times 10 to the negative fifth. I'm always looking to not do a quadratic equation if I can help it. So if I take this number and I multiply it by 1,000 and it's still less than this number, I can say that x is negligible. All right, and this times 1,000 is 1 times 10 to the negative 1. Okay, so 0.01, that is still less than this. So the initial concentration is more than 1,000 times my Ka. So I can say that plus x and minus x is inconsequential here. And then it makes it easier to calculate x. I got that x was equal to 5.77 times 10 to the negative 4. If I take the negative log of both sides, I get that the pH, and so x was equal to the hydrogen ion concentration. So when I take the negative log of the hydrogen ion concentration, I get pH, and I got 3.24. Now that makes sense. It's a weak acid solution, so I should get an acidic pH, but it's a weak acid solution, so I'm probably not going to get a pH of 0. I'm going to get, something between 0 and 7. All right, so that's how we would do a polyprotic acid-base titration, looking at it from starting with the base and adding, so basically a diprotic base, a base that can get 2 hydrogens, and adding a strong acid. We calculated point A, which was 0 milliliters added. We calculated a point between point A and point B, which was 1.5 milliliters added. We calculated point B, which was 5 milliliters added. To do those, this was just a weak base problem. This was a buffer problem, so we used Henderson-Hasselbalch. At 5 milliliters, it was halfway to an equivalence point, so we said that the pH was equal to the pKa. At C was when 10 milliliters was added, and that was our equivalence point. At our equivalence point, we used the equation that we had developed during the systematic treatment of equilibrium, which was K2 times K1 times the formal concentration plus the formal concentration, plus K1 times Kw over the formal concentration plus K1, and that's a square root. Okay, so that's how we calculated the pH at 10 milliliters. Then we calculated the pH at D, which was 15 milliliters, which was at a half equivalence point again, and the pH was equal to the pKa. And then we just did point E, which is a weak acid equilibrium. We used an ICE table to do that one. Now, in the original titration curve that we looked at, I'm going to draw in green here, you can see that there's this really nice 2 equivalence points. There's an equivalence point at C and an equivalence point at E. But for a lot of polyprotic systems, like diprotic systems, what happens is more like this one here, where we only get one equivalence point and then the other one just kind of smooths out. And it's almost that like just the first equivalence point is shown. That happens a lot because just the first equivalence point, the K is a lot higher for the first part of the equilibrium than it is for the second part of the equilibrium. And so a lot of time we only see that first equivalence point, and the second equivalence point just kind of smooths out. So this happens depending on the relative strength of the Kas or Kbs. And so kind of in observation, when we're doing this in lab, sometimes it's really only possible to observe the first equivalence point. The good news is if we know if we can measure that first equivalence point, we know that the second equivalence point would be 2 times the volume. So we can still do some calculations as long as we can find, kind of by observation, one of the equivalence points. All right, so in this video, in this chapter, we started with finding the pH of diprotic systems. We talked about how to find the pH when it's the totally protonated form. We talked about how to find the pH when it's in its totally basic form, and then we talked about how to find the pH when it's in its intermediate form, which is when we need to use the systematic treatment of equilibrium, or with a few assumptions, we come down to kind of an easy equation. And then we moved on to titration curves for polyprotic systems, and we learned how to calculate the pH for different points. Those points are very related to the points that we learned for monoprotic systems. So we have buffer regions, we have equivalence points, we have halfway between the equivalence points. All those, if we keep them in mind, are kind of special and can reduce the amount of calculations that we have to do. But kind of keeping track of them overall and knowing where you are in the titration can help you know whether you can make those shortcuts or not.